Howdy, it's Mr. Russell, and we're here to talk about the acid-base theories, particularly the Arrhenius theory. The Arrhenius theory is also known as the traditional theory of acids and bases. That's where acids will start with H or H plus, and bases will end in OH minus or OH minus. There is also the Bronsted-Lowry theory, which we will talk about in the next video or the next lesson. And that says that acids are proton donors and bases are proton acceptors. So we'll save that for the next time, though. There is also a Lewis theory, and it has to do with the electrons, but that is not tested in this course, and it's not tested in AP chemistry either. That's more essential to organic chemistry. So Svante Arrhenius was born in 1859. He received the Nobel Prize in 1903. He was the first one to actually really come up with this idea that things could break down into different ions, where acids could break down into hydrogen ions and bases would break down into hydroxide ions. Okay? So an Arrhenius acid is a chemical compound that increases the concentration of the hydrogen ions, which is the H plus ion in aqueous solution. Now the H plus ion, when reacted with water, will produce H3O plus. So what I mean is we have an extra hydrogen hanging around here, and when it comes in contact with water, we get H3O. You guys can see that it's just water with an extra hydrogen and also an extra positive charge. So this term H3O and H plus can be synonymous and they can be interchanged. If we have nitric acid, that's HNO3, that's an Arrhenius acid, comes in contact with water, we get the hydronium ion and the nitrate ion swimming around. Again, with HCl, same thing, it comes in contact with water, we get hydronium and the chlorine ion floating around. Now, when ionic compounds separate into multiple ions, it is called dissociating, okay? This may also be called dissociation or ionization. I'll be talking about that later. So here we have the ionization of an acid, we have the ionization of a base, and then here's the ionization of a salt. So it's really any ionic compound that's breaking up into ions or dissociating. So to show the equations that show the Arrhenius behavior, this is in your notes on page 4 for example 1. Now it's going to seem weird. I'm actually going to do example B first. This is nitric acid. So if we have nitric acid is HNO3 and reacts with water, it produces the hydronium ion and the nitrate ion. Okay, piece of cake. Now, sulfuric acid is a good one because it has, this is going to be H2SO4. So we have two hydrogens here, can react with water. So now what will happen is we'll pull one hydrogen away and make H3O plus, and then we have HSO4. This should be a 4 right here with a minus charge. Now, we still have a hydrogen attached to this, so it can dissociate one more degree to make the 2 H3O plus and then the SO4 2 minus. So this sulfuric acid actually has two hydrogens to give when nitric acid has one hydrogen to give. We also call hydrogens protons, so this would be called a monoprotic acid. And then here, this would be called a diprotic acid, okay? Those terms will be important later. Now we have the Arrhenius bases, which an Arrhenius base is a substance that increases the concentration of hydroxide ions, or the OH, in aqueous solutions. So, hold on, let's go back. We have sodium hydroxide. Now we're going to assume it's dissolved in water. Now water doesn't really fit on the left side or the right side, so I'm putting it over the arrow. This is dissolved in water. So it will produce the sodium ion and the hydroxide ion. Both of them are aqueous solutions. So that's why H2O is over the arrow. It's not really a catalyst, it's just being dissolved in water. Okay. Now, so to show the equations for the Arrhenius behavior of potassium hydroxide, that's KOH. So just draw water on top of an arrow and we get K plus and OH minus. For calcium hydroxide, we have calcium and two hydroxides. So it will dissolve in water to make a calcium 2 plus and two hydroxides. Okay. Now in here, we're supposed to draw a particle view. This is example 3 on page 5. In beaker A, you want to draw an acid with HA. A would be any generic acid, any generic anion, dissolved in water. And in beaker B, draw a base with any generic cation with hydroxide, dissolved in water. So for beaker A, it would look like this. What is going on is that all the ions are broken up and they're all kind of swimming around. And that's the best way I can describe that. They're all occupying in this space in a homogeneous zone, meaning that they're all spread out evenly. In beaker B, they're all spread out evenly again. They dissociate completely. Arrhenius acids and Arrhenius bases will always dissociate 100%. So this is dissociation. Now, the neutralization reactions are going to be a good one. So what is going to go on is when we have an acid and a base that come in contact with each other, they will neutralize each other. And they will always produce a salt and they will produce water. Okay. Now, when I say a salt, I don't just mean sodium chloride. I mean any ionic compound that is not an acid or a base. So what's going to happen is the sodium hydroxide is going to dissociate into these two ions, which we just covered before, and the hydrochloric acid is going to dissociate into these ions as well. It's going to react with water to make H3O and Cl minus. Now we'll take all of these products right here, and these are actually the ionization of the reactants. What all they are is these two reactants split up into ions. We have this compound will make two different ions, and this compound will make two different ions. We have a total of 4 ions right here. So I will draw a total of 4 ions right here. That's what this line is right here. Okay, so all 4 of these are here and they're swimming around all together in the same solution. What will happen is the H3O and the OH will pair up. We have, when we have hydronium and hydroxides, they will even each other out and they will produce water over here. So what we're actually going to see is we have 3 hydrogens and another hydrogen that makes 4 hydrogens. And then we have an oxygen and an oxygen that makes 2 oxygens. So the formula for water is H2O. So that's the right ratio. We have 2 H2Os, right? We have 2 waters. Now the sodium is still unchanged and the chlorine is left unchanged. What we call these are things that did not change, or we call these spectator ions. They did not actually participate in the reactions. They're the same on the left side and the right side. Now, what is convenient about that is that we don't write them in the final net ionic equation in this last equation. We just have the ones that actually change. The acid and the base created 2 waters. That was the overall actual reaction. Okay, everything else was just kind of there as a placeholder. Okay, Now, the good news is that you don't have to do that all the time. That was just me to explain what's going on. So, in an aqueous solution, the neutralization is the reaction of the hydronium ions and the hydroxide ions to form the water molecules. Now, salts are also produced, okay? And now these are known as the spectator ions because they do not participate in the reaction and are not changed. So what we actually have, and you'll see this on your homework, is that an acid plus a base will always yield a salt and water. Okay, so keep that in mind. And this is always true. So let's walk through our examples, and these examples are going to be on page 6. Example number 4 says to predict the products of the following acid-base reactions. What you have is you have nitric acid and potassium hydroxide. Well, we want to take the front side and the last side. These are all double replacement reactions, by the way. All acid-base reactions are double replacement reactions like we've covered in the past. So you take the first term and the last term, you pair them up together, and you get water. Okay, we have H and OH makes H2O. And then you take the inside terms, which is K and NO3. Now be aware that the order will be backwards. The cation will be here, and it should get named first. So we'll take K, NO3. All right, we'll have potassium nitrate. And that's the reaction. Okay. Now, please note that water is a liquid, and then KNO3 is aqueous. All right, that a lot of students want to make water as aqueous, and that doesn't make any sense. Water is not dissolved in water. Water is just a pure liquid, but potassium nitrate is aqueous. I did not write that on there. Now, on this one, we have calcium hydroxide and sulfuric acid. So the calcium and the sulfate right here. Oh, excuse me. We'll take the inside terms first. We have 2 hydrogens and 2 hydroxides. So 2 hydrogens, 2 hydroxides make 2 waters. And then the outside terms, we have calcium and sulfate will make calcium sulfate. Calcium is a 2 plus charge, sulfate is a 2 minus charge, so they all cancel out. We don't have to add any extra subscripts. Now, to determine the acid and base that would have made the following salt, we would call this the parent acid and the parent base because that's where they came from. What you should do with this is try to think of the acid and base that would have made this salt. All 3 of these are salts. So recall that an acid comes from H plus and a base ends in OH. So the cation, hold on, I'm sorry, this anion right here, the second, the one that's named on the right, should have been paired from the acid, and the cation should have been paired from the base. All right, that's helpful information to know because the cation is the positive charge. So now what is going to be helpful is this is just going to be HCl, all right? And because there were 2 chlorines that were made, right, in this last one, we would have actually needed 2 hydrochloric acids. And then over here, we had 2, we needed 2, I'm sorry, this made magnesium hydroxide. Okay. This is the parent acid, and this is the parent base. Now here, we have lithium and phosphate. Now, the parent acid is going to be phosphoric acid because that would have been H plus would have had to make PO4. And then the parent base would have been lithium hydroxide. And then for aluminum bromide, the parent acid would have been HBr, and then the parent base would have been aluminum hydroxide. Okay, you'll have to stare at that to really try to make sense of that. but it does make sense if you remember, if you try to work backwards from the previous neutralization reactions that we did, okay? So you now need to practice this. This is in your worksheet packet. You should have this, and it should be the first page of your worksheet packet. So I want y'all to do this front and back for homework tonight. A lot of this stuff was straight out of the video and the notes. All right, good luck, guys.